Free radical halogenation is one of the most important reactions for learning radical chemistry. Up until now, most of the reactions we have discussed involved nucleophiles, electrophiles, carbocations, and electron pair movement. But radicals are different. Radicals contain an unpaired electron. Because of this, radical reactions use single-headed arrows, sometimes called fishhook arrows, instead of the double-headed arrows we use in ionic and polar mechanisms. Today we will learn the mechanism of free radical halogenation, the difference between chlorination and bromination, and why fluorine and iodine are generally not used. Let's start with the overall reaction. In free radical halogenation, an alkane reacts with chlorine or bromine in the presence of light or heat. For example, methane plus chlorine gives chloromethane plus hydrochloric acid, or methane plus bromine gives bromomethane plus hydrobromic acid. The important thing to notice is that a hydrogen atom has been replaced by a halogen atom. That is why this reaction is called a substitution reaction. Now let's discuss the mechanism. Free radical halogenation occurs in 3 stages: initiation, propagation, termination. Let's start with initiation. During initiation, light energy breaks the chlorine-chlorine bond, or bromine-bromine bond. This process is called homolytic cleavage. 1 electron goes to each halogen atom. The result is 2 halogen radicals. For chlorine, a neutral chlorine molecule produces 2 chlorine radicals, and for bromine, a neutral bromine molecule produces 2 bromine radicals. Now we move to propagation. This is where the chain reaction begins. Step 1. The halogen radical removes a hydrogen atom from the alkane. This creates hydrogen chloride or hydrogen bromide and forms an alkyl radical. Step 2. The alkyl radical reacts with another halogen molecule. This creates the alkyl halide product and regenerates another halogen radical. The newly formed radical continues the chain reaction. This is why one initiation event can produce many product molecules. Finally, we have termination. Termination occurs when 2 radicals collide and combine. Examples include halogen radical plus halogen radical, alkyl radical plus halogen radical, alkyl radical plus alkyl radical. Since radicals are consumed, the chain reaction stops. Now let's discuss the most important exam concept: the difference between chlorination and bromination. Students often memorize that bromine is more selective, but understanding why is much more useful. Chlorination is very reactive. In its energy diagram, chlorination's 2 propagation steps are both exothermic. The activation energy for the first step is very small, meaning the reaction can begin very easily and happens fast. Because it is so reactive, chlorine radicals do not strongly discriminate between different hydrogens. Even though a tertiary carbon is technically preferred, chlorine reacts so violently that it often just strikes whatever hydrogen it hits first. As a result, chlorination often produces complex mixtures of products. Bromination is less reactive and much more controlled. Bromination is slower than chlorination because its first propagation step is endothermic. This endothermic step causes the activation energy to be much higher. Note that the overall net reaction from both propagation steps combined is still exothermic, but that difficult first step changes everything. Because the first step is endothermic, the transition state closely resembles the final radical intermediate. This means the stability of the forming carbon radical determines how fast the reaction can cross that energy barrier. Because it is less reactive, bromine radicals are much more selective. They strongly prefer forming the most stable radical possible. This usually means bromination occurs almost exclusively at the most substituted carbon, giving you one major product instead of a messy mixture. Before we start predicting bromination products, we need to talk about radical stability, because that's really what controls where bromination occurs. As a general rule, radicals become more favorable as they become more stable. The stability order you'll want to remember is benzylic radicals are the most stable, followed by allylic radicals. After that come tertiary radicals, then secondary radicals, then primary radicals, and then methyl radicals. Finally, vinylic radicals are the least stable and are generally very unfavorable. Why is this important? Because bromination is highly selective. Instead of reacting at many different positions, bromination strongly prefers the pathway that forms the most stable radical intermediate. So whenever you're asked to predict the major bromination product, your first question should be, which hydrogen gives me the most stable radical when it's removed? Once you identify the most stable radical, you've usually found the major product. That's what makes bromination much more predictable than chlorination. Chlorination often gives mixtures because chlorine is so reactive, but bromination tends to point you directly toward the most stable radical intermediate. A simple way to remember this is chlorination is fast but messy. Bromination is slow but selective. Now let's discuss fluorine and iodine. Students often wonder why we focus on chlorine and bromine. Why not fluorine or iodine? Fluorination is extremely exothermic. The reaction releases so much energy that it is difficult to control. In many cases, the reaction becomes explosive. Because it is too reactive, fluorine is generally not used for free radical halogenation. Iodination has the opposite problem. The reaction is generally endothermic. The propagation steps are unfavorable, and the radical chain cannot effectively continue. As a result, iodination usually does not occur under normal conditions. This leaves chlorine and bromine as the useful halogens for free radical substitution. Now let's work through some examples. Example 1, chlorination of propane. Let's start with propane reacting with chlorine under light. Because chlorine is highly reactive and not very selective, chlorination can occur at either a primary hydrogen or the secondary hydrogen. First, we have the initiation step. Under light, the chlorine-chlorine bond breaks homolytically to form two chlorine radicals. Next, let's look at the first propagation step. A chlorine radical abstracts a hydrogen atom from propane. This can occur at either a primary carbon or the secondary carbon, producing hydrochloric acid and either a primary propyl radical or a secondary propyl radical. For the second propagation step, the propyl radical reacts with another chlorine molecule. A carbon-chlorine bond forms, and another chlorine radical is regenerated so the chain reaction can continue. Looking at the products, both 1-chloropropane and 2-chloropropane are formed. Because the secondary radical is slightly more stable than the primary radical, 2-chloropropane is usually the major product. No chiral centers are formed in this reaction. Finally, in the termination step, two chlorine radicals combine to form a chlorine-chlorine bond, removing radicals from the reaction mixture. Example 2, chlorination of 2-methylpropane. Now let's examine 2-methylpropane reacting with chlorine under light. In this molecule, chlorination may occur at the tertiary hydrogen or at any of the 9 equivalent primary hydrogens. First, we have the initiation step. Light causes the chlorine-chlorine bond to break, generating two chlorine radicals. Next, let's look at the first propagation step. A chlorine radical can remove either the tertiary hydrogen or a primary hydrogen. This produces either a tertiary radical or a primary radical. For the second propagation step, the radical reacts with chlorine to form a carbon-chlorine bond while regenerating another chlorine radical. Looking at the products, both 2-chloro-2-methylpropane and 1-chloro-2-methylpropane are formed. The tertiary product is favored because the tertiary radical is more stable, although a noticeable amount of the primary product is still produced. Finally, in the termination step, two chlorine radicals combine to form a chlorine-chlorine bond. Example 3, chlorination of pentane. Next, let's look at pentane. Because pentane contains several unique types of hydrogens, multiple substitution products are possible. First, we have the initiation step. The chlorine-chlorine bond breaks under light to form two chlorine radicals. Next, let's look at the first propagation step. A chlorine radical can abstract a hydrogen from the first carbon, the second carbon, or the third carbon. Each pathway produces a different radical intermediate. For the second propagation step, each radical reacts with chlorine gas to form a carbon-chlorine bond and regenerate another chlorine radical. Looking at the products, 1-chloropentane, 2-chloropentane, and 3-chloropentane are all formed. Because chlorine is relatively unselective, all three products are obtained. Now let's discuss the stereochemistry. 2-chloropentane contains a new chiral center, so both the R and S enantiomers are produced. Finally, in the termination step, two chlorine radicals combine to form a chlorine-chlorine bond. Example 4, chlorination of cyclohexane. Now consider cyclohexane reacting with chlorine under light. Since every hydrogen in cyclohexane is equivalent, only one substitution product can form. First, we have the initiation step. The chlorine-chlorine bond breaks under light to produce two chlorine radicals. Next, let's look at the first propagation step. A chlorine radical removes any hydrogen atom from cyclohexane. Regardless of which hydrogen is removed, the same cyclohexyl radical is produced. For the second propagation step, the cyclohexyl radical reacts with chlorine gas to form a carbon-chlorine bond. Looking at the products, only chlorocyclohexane is formed. Because every carbon in the ring is equivalent, only one constitutional isomer is possible. No chiral centers are created. Finally, in the termination step, two chlorine radicals combine to form a chlorine-chlorine bond. Example 5, chlorination of methyl cyclohexane. Our final chlorination example is methyl cyclohexane. Because there are several different types of hydrogens in this molecule, many different substitution products are possible. First, we have the initiation step. The chlorine-chlorine bond breaks under light to generate two chlorine radicals. Next, let's look at the first propagation step. Hydrogen abstraction can occur at several different carbons in the molecule, leading to several possible radical intermediates. For the second propagation step, each radical reacts with chlorine to form a substitution product while regenerating another chlorine radical. Looking at the products, several constitutional isomers are formed. Next, we should look at all our products and see if we made any new chiral centers. For the new chiral centers created, both the R and S enantiomers will be produced. Finally, in the termination step, two chlorine radicals combine to form a chlorine-chlorine bond. Now, let's look at some bromination examples. Example 1, bromination of propane. Now, let's compare chlorination to bromination. Propane reacts with bromine under light, but unlike chlorination, bromination strongly favors formation of the more stable radical. First, we have the initiation step. The bromine-bromine bond breaks under light to form two bromine radicals. Next, let's look at the first propagation step. A bromine radical removes the secondary hydrogen from propane, producing the more stable secondary radical. For the second propagation step, that radical reacts with bromine to form a carbon-bromine bond and regenerate another bromine radical. Looking at the products, 2-bromopropane is the major product. No stereocenters are produced. Finally, in the termination step, two bromine radicals combine to form a bromine-bromine bond. Example 2, bromination of 2-methylpropane. Next, let's examine 2-methylpropane. In this reaction, the tertiary hydrogen is strongly favored because its removal produces a tertiary radical. First, we have the initiation step. The bromine-bromine bond breaks under light to form two bromine radicals. Next, let's look at the first propagation step. A bromine radical removes the tertiary hydrogen, generating a tertiary radical. For the second propagation step, that radical reacts with bromine to form a carbon-bromine bond. Looking at the products, 2-bromo-2-methylpropane is overwhelmingly the major product. No stereocenters are formed. Finally, in the termination step, two bromine radicals combine to form a bromine-bromine bond. Example 3, bromination of methyl cyclohexane. Now let's look at methyl cyclohexane. Bromination occurs almost exclusively at the position that generates the most stable radical intermediate. First, we have the initiation step. Two bromine radicals are formed. Next, let's look at the first propagation step. A bromine radical removes the hydrogen from the most substituted carbon, producing the most stable radical. For the second propagation step, the radical reacts with bromine to form a carbon-bromine bond. Looking at the products, the major product comes from substitution at the carbon that originally formed the most stable radical. We create the most stable product, 1-bromo-1-methyl cyclohexane. Finally, in the termination step, two bromine radicals combine to form a bromine-bromine bond. Example 4, bromination of ethyl cyclopentane. Next, consider ethyl cyclopentane. We want to add bromine on the most substituted carbon, which will take the tertiary hydrogen. First, we have the initiation step. The bromine-bromine bond breaks to generate two bromine radicals. Next, let's look at the first propagation step. A bromine radical removes the hydrogen that produces the most stable radical intermediate. For the second propagation step, the radical reacts with bromine and forms a carbon-bromine bond. Looking at the products, we form one major product, 1-bromo-1-ethyl cyclopentane. Finally, in the termination step, two bromine radicals combine to form a bromine-bromine bond. Example 5, bromination of 3-methylpentane. For our final example, let's examine 3-methylpentane. As with most bromination reactions, the most stable radical pathway dominates. First, we have the initiation step. Two bromine radicals are formed. Next, let's look at the first propagation step. A bromine radical removes the tertiary hydrogen, producing a tertiary radical. For the second propagation step, the tertiary radical reacts with bromine, forming a carbon-bromine bond and regenerating another bromine radical. Looking at the products, 3-bromo-3-methylpentane is the major product. Finally, in the termination step, two bromine radicals combine to form a bromine-bromine bond. Now let's discuss some common mistakes students make. Mistake number 1, using double-headed arrows. Remember that radical mechanisms use single-headed fishhook arrows because only one electron is moving at a time. Mistake number 2. Forgetting the light or heat conditions. Without light or heat, the initiation step cannot occur. Mistake number 3. Treating chlorination and bromination as though they behave the same way. Chlorination produces mixtures because chlorine is highly reactive and relatively unselective. Bromination is slower but much more selective. Mistake number 4. Ignoring radical stability. Whenever you're predicting a major product, ask yourself which radical intermediate is most stable. Tertiary radicals are favored over secondary radicals, and secondary radicals are favored over primary radicals. Mistake number 5, trying to use iodine. Iodination is generally unfavorable and does not proceed efficiently under free radical conditions. So if you remember only one thing from this video, remember this. Free radical halogenation always proceeds through initiation, propagation, and termination. Chlorination is fast but messy. Bromination is slower but far more selective. And when you're trying to predict the major product of a bromination reaction, simply identify the most stable radical intermediate, because that's almost always where the reaction occurs.